7.2 area in the plane. Example 1, find the area under the line y equals negative x from x equals 0 to x equals 1. This is review. When we're finding area under the curve or the line or whatever, we're going to integrate. So from 0 to 1, we're finding the area under the line x or negative x. Okay, so same old, right? You would add an exponent, so now that's squared, and then divide by that new exponent. And now this is my integral, and I'm evaluating it from 0 to 1. So I would plug in 1, so I have negative 1/2, and then I would subtract whatever I get when I plug in 0. So then my answer is negative 1/2. All right, example 2. Find the area under the curve from x equals 0 to x equals 1. Same thing, if I want to find the area, I'm just going to integrate. Now, they're not specifying total area, right? So I'm just finding the net area. And the net area, I don't have to worry about the negatives, right? The parts that are negative. So integrate, I'm going to add an exponent, divide by the new exponent, plus 2 becomes 2x. And then I'm evaluating this from 0 to 1. So I would plug in the 1, I get 1/3 plus 2. And then I would plug in the 0, and I get 0 plus 0. So then I have 1/3 plus 2. If I find common denominators, the least common denominator, 6 is their common multiple, right? So 1/3 becomes 2 over 6, and 2 becomes 12 over 6. And so now I have 14 over 6, which of course can be simplified to 7/3. You know what? I don't know why I did that, but I did. This could have been 1/3 plus 6/3. I don't know why I did that. Okay. So following areas between curves. So now instead of just finding the area underneath the curve and the x-axis, we're looking for the area between curves. So for example, here I have two curves. I have F and I have G. Now notice, we're looking for the area between F and G, but just between A and B. So we're looking for this right here. Now, the idea of area up to this point for us has been like this. If this is the function that I'm looking at, and I want to find the area from a certain interval from A to B, the area we would find is all of this underneath the curve all the way up to the x-axis. We wouldn't pass the x-axis. So that would be the area that we would be looking for. So that right there is the area for F from A to B. Now, the area underneath G, so here's G, the area underneath G from A to B is this right here. So now what we're doing in today's lesson is we're going to use these two ideas, or not two, it's just one, sorry. We're going to use this idea, right? And we're going to combine them in a way that instead of giving us all of this and or just this, what it's going to give us is this. Now think about it. Notice how f is the function on top for the most part, right? And it has the bigger area. Well, g is mostly the bottom part. And if I did this, okay, so this is the whole area, right? If I really just want the area or the space in between the two graphs, I would take the whole area, which is blue, and then I would subtract this green part of it. And subtracting the green part would get me just the red part. Okay, you see? So I could find just the red part, right? Which is what I would find if I took all of the blue. This is all of the blue here. And then I took the green, took that away. What would be left is the red. And that's the idea of today's lesson. If I want to find the area in between two graphs, two equations, two curves, um, I'm going to take the curve on top, right, the one with the most area, and then I'm going to subtract the curve on the bottom, the one with oh, I'm sorry. It's not necessarily more or less. In this case, it is. But it covers more of the graph anyway. And then I would find whatever it is actually in between the two. So this is the formula we're using. Area is top curve minus bottom curve. And of course, my limits depend from where to where. Okay, so example 3. Find the area of the region bounded by the graphs. Now, if you notice, if you pay attention, these two equations should look familiar. And that is because this is from example 1. And this one is from example 2. So technically, we've already found the areas. So I just want to go ahead and practice using the formula, which is the top curve minus the bottom curve. Now, so if you look here, the top curve is x squared plus 2. And the bottom curve is the negative x. So what we would be doing, we'll first need to find our limits from where to where. So from 0 to 1, right? This is from left to right. My lines aren't very straight today. So from 0 to 1. And then it's the top curve, which is x squared plus 2 minus, let's see, the bottom curve, which is negative x. Now, like I said, we've already actually done these integrals, kind of. The integral for x squared plus 2, if you look back at example 2, our answer was 7/3. So then minus, and then for negative x, in the integral we did in example 1, it was negative 1/2. Obviously, I used the same limits for both examples as this example, right? I just wanted to review finding regular area and then use it for this example also. So when you integrate the two equations and you plug in 1 and you plug in 0, we get 7/3 and we get negative 1/2. So now the idea is that I'm supposed to subtract these. So I'm actually doing 7/3 plus 1/2. Common denominator would be 14/6 plus 3/6. So my area underneath, or between, sorry, in between the two curves is 17/6. And that accounts for this right here. Now the idea is, in this picture, oh, hold on. In this picture, right, this area that we just found. So let's see, the blue graph, the one on top, takes care of all of this area, right? That's how, when you find the integral, when you're finding the area of one equation, it gives you all of the area underneath the curve all the way to the x-axis. Well, the green does the area between the curve and the x-axis. So that would take care of this part right here. And this is negative, right? Makes sense. But I'm actually putting them together. So the negative 1/2 becomes, added because I was subtracting. So let's see. This up here was 7/3. and the one down here was negative 1/2. So I joined them together, and I got 17/6. Okay, so this is one example of when it's not always subtracting really. Yes, did we subtract? Uh-huh. But by subtracting, we ended up making that negative area positive, which is what we want. Okay, so here in reality, we added. Okay, example 4. So I think this is going to be the only example. You know what? No. I'm going to do example 5 the whole way out. Example 4 and 6, you can do in your calculator if you like. Um, because this is just a technique, it's not so much integrating. We should know how to integrate by now. Some of us still struggle, but it's really, I mean, at this point, we should be able to integrate just regular equations without a problem. So find the area of the region bounded by f of x and g of x. Okay, so here, f of x is the top one, right? So essentially, this would give me the area, let's see, all of this area, get me all of this, and then for the bottom part to take care of that. Sorry. It'll give me all of this area. Okay. And it would get me, oh boy, it would get me this area. Okay. And then there's like a little piece right here. Um, now, g of x. G of x is this line right here. And g of x would find me this area. And all of this area, etc. So now notice, um, we are looking for the area bounded by the two graphs. That means the area in the middle. And that would be from here to here. This is the area that's in the middle, right, in between two graphs. Now, as you can see, wherever the blue and the red overlapped, I'm not including that. Okay? And that's because they're going to cancel each other out. That's why I don't have to worry about that. The blue and the red does cancel each other out. So essentially, I'm putting together the blue part that's up here, this blue part. I'm joining that with this red part. And anywhere that the red and the blue overlapped, that gets canceled out. Okay? All right. So that looks a mess, but I'm just trying to explain. And again, I would encourage you to use your calculator on this to get a little bit of practice in entering um, integrals into the calculator, but we're probably professionals at that by now. So, it's going to be from where to where. So here I see they touch at -2, and they touched at 1. And then the top curve, I'm going to write that one first. So 2 minus x squared, because that gets subtracted, or sorry, that's the number I'm going to subtract from. So 2 minus x squared minus, and then g of x. And g of x is just x. So there's my integral. And then you can pop that into your calculator. And you should get 9/2 or 4.5. Okay? All right, example 5. I'm going to do this one the whole way out. The sine and cosine curves intersect infinitely many times, bounding regions of equal areas. Find the area of one of these regions. So they just want us to find the area from here to here because that's where the equations or the graphs intersect. And so really all I want is this little piece right here. Okay, so I need to figure out where is this that they intersect. So that should be pi over 4, right? Halfway between 0 and pi over 2. And then also here, which is halfway between pi and 3 pi over 2. Or if you think about it, 180 and 270. Um, so you can also be like, okay, this is 1/4, this is 2/4, 3/4, or 4/4, and 5/4. So that's 5/4 pi. All right. If you look, sine is the function on top, and cosine is the function on bottom. So sine x minus cosine x dx. My limits are from pi over 4 to 5 pi over 4. So now we integrate. The integral of sine is cosine. But let's see, when I derive cosine, I get negative sine. This sign is not negative, so that means the original cosine should have been negative in order to get rid of the negative. And then minus, and then the integral of cosine is just sine. And then we're evaluating this from 5 pi over 4 to pi over 4. All right, unit circle time, right? In the unit circle, pi over 4 is right here. And the coordinates are square root of 2 over 2. 5 pi over 4. So let's see, this is 1, 2, 3, 4. There you go, 5. 5 pi over 4 is right there. And the coordinates are the same, only that in the third quadrant, everything's negative. So it's going to be negative square root of 2 over 2. All right, so I'm going to plug in 5 pi over 4. So negative cosine of 5 pi over 4 minus sine of 5 pi over 4. And then that's minus. And now I'm going to plug in pi over 4. Negative cosine of pi over 4 minus sine of pi over 4. Okay, so let's see. The cosine is the x coordinate. So recall that I did just say, I just didn't write it. The coordinates over here are square root of 2 over 2, but negative, and negative square root of 2 over 2. Oh, that's messy. Let's move this a little bit over. Negative square root of 2. 2. Goodness gracious, you can't even tell they're negatives. Okay, so this is negative square root of 2 over 2. Minus, the sign of is still a negative square root of 2 over 2. Minus, and then, okay, negative cosine pi over 4. So see cosine, again, x coordinate. So negative square root of 2 over 2 minus square root of 2 over 2. Now, it would probably be easier to take care of all the negatives everywhere. For example, this negative should get distributed. So this is positive square root of 2 over 2, positive square root of 2 over 2. Again, negatives should become positive, and then this negative makes that negative positive. So I have another positive square root of 2 over 2 plus another positive square root of 2 over 2. So what do I have? I have 1, 2, 3, 4 square roots of 2 divided by 2, which is basically 2 square roots of 2, right? Because the 4 and the 2, they can simplify. So this is 2 and this is 1. And there's my answer. All right, example 6. Find the area of the region between the graphs. And so this is another one that you can do on your calculator. Okay, last example is a little different. We are still going to find the area between the graphs, but if you analyze the graphs itself, you will see that sometimes one equation, one of the functions is on top, but then if you keep looking or following the graph, this graph is now underneath. It's the one on the bottom, and then the other is now on top. So I have two functions, f and g. And so like if we look at this picture, on the left part here, from -2 to 0, this graph is clearly the one on top. Well, this graph is f, okay? So f is on top from -2 to 0. But then from 0 to +2, f is no longer on top, okay? It is now the bottom curve. And now the one that is on top is g. Here's g. G is the one on top, okay? So that does make a difference. Uh, what we're going to do here in these instances is that we're going to make two separate integrals, and then we're just going to add those areas together. All right, so let's see, it was from -2 to 0, f is on top. So from -2 to 0, it's going to be f of x minus g of x dx. And then we're going to add that to another integral. And this integral is going to be from 0 to +2. And in this region, g is on top. So it'll be g of x minus f of x dx. Now notice how I'm not writing the long equations because I'm encouraging you to do this in your calculator. You can do it by hand. It's not impossible, right? But when you do plug it into the calculator, and please remember it is math number 9. Okay, you're going to plug in the limits, and then you're going to make sure that you plug in this function first, and then you subtract the other function. So what I would do is I would do this one in the calculator first, and you end up getting 12. And then I would do this one in the calculator. Coincidentally enough, you also get 12. Let me write that blue. And then you would add them together, and you would get an area of 24. Alright, so that was today's lesson. There is another part to this section that involves the same idea, just different scenarios, I suppose. Here's your homework. 1, 2, 3, 4, 5 problems, page 380. Please try to do them. I'll encourage the use of the calculator. Okay, you should know how to integrate by now, and some of you don't. You have to be able to do that by hand. And next class we will be going over the AP multiple choice review that you did last class, the 10 questions, among some other things. All right.